In this video, we're going to solve equations given functions using the quadratic formula. Let's practice this next situation. So we have let f of x equals 3 minus x over 4 and g of x equals 1 over 4x. Find all x for which f of x equals g of x. Basically what this is saying is we need to find where the functions equal each other or where they intersect each other by setting the two functions equal. If I set them equal to each other, I'll have 3 minus x over 4 equals 1 over 4x. This looks like a rational equation, in which case I'll find an LCD. The LCD is 4x, and so I'll multiply both sides of this equation by the LCD, 4x over 1 on both sides. When I divide out the common factors, this will clear my fractions in the equation, and I'll be left with 3 minus x times x equals 1. If I multiply the x into the parentheses on the left, I'll have 3x minus x squared equals 1. And then if I set my quadratic equal to 0, I'll have x squared minus 3x plus 1 equals 0. This is quadratic in form, in which case I can factor it, but only if it comes out nice. Otherwise, I would use the quadratic formula. We are kind of given a hint here. Using the quadratic formula, x is equal to negative b plus or minus the square root of b squared minus 4 times ac all over 2a. I will then substitute a equals 1, b equals negative 3, and c equals 1. This gives me x is equal to 3 plus or minus the square root of negative 3 squared minus 4 times 1 times 1 all over 2 times 1. Simplifying, I get 3 plus or minus the square root of 9 minus 4 all over 2. And I'm just going to rewrite this over here. Simplifying, we have x is equal to 3 plus or minus the square root of 9 minus 4 is 5, and 5 is prime, all over 2. Notice that I cannot reduce anything. Now let's look at this next example. G of x equals 2 over x plus 2 over x plus 3. And we need to find all values of x such that g of x equals 1. Basically, this is saying instead of g of x, replace the g of x with a 1. So we'll rewrite this. 1 is equal to 2 over x plus 2 over x plus 3. Again, our LCD will be x times x plus 3, and so I'll multiply both sides of my equation by that LCD. X times x plus 3, x times x plus 3. And now I can reduce the denominators on the right side of the equal sign. On the left, 1 times x plus 3 will just be the LCD. But on the right, my x will divide out of the 2 over x, and I'll just be left with 2 times x plus 3. And my second fraction, or rational expression, 2 over x plus 3, the x plus 3 will divide, and I'll just have 2x. Distributing, I will get x squared plus 3x on the left. On the right, I'll have 2x plus 6 plus 2x. It's usually easier to factor and also to calculate using the quadratic formula if your leading term has a positive coefficient. It's not required, but that's just kind of my pattern that I stick with. And so I'll have x squared plus 3x, bringing my other terms over. I'll have minus 4x, combining the two x's on the right side of the equal sign, and minus 6 equals 0. Combining like terms, I'll have x squared minus x minus 6 equals 0. Now, I could check first, and you should always do this, check to see if you have any factoring that you can do before you use the quadratic formula. It might come out nice. You never know. So give it a try first. I'm going to try x minus 3, x plus 2. And if I FOIL that just to check, checking gives me x squared minus 3x plus 2x minus 6, which will combine, and I'll get an x squared minus x minus 6. So those two factors do work. I'm not going to need to use the quadratic formula if I can factor it without worrying about the quadratic formula. It's that fewer steps. Now, set each one of my factors equal to 0. I get x equals 3 and x equals negative 2. Now, the last step is to make sure that the values that you find for your solution here actually work in the equation that you started with. So if I substitute 3 into this equation up here, I will not get any vertical asymptotes or undefined denominators. So x equals 3 is a good solution. And x equals negative 2. If I substitute negative 2 into either of these denominators, x equals negative 2 works as well.